Hi and hello guys, let me introduce myself first. Me as Hani Suhada binti Musa from group 2, and these are my team members Luke and Hui, Intan, Haris and Melvin. All of us will present about burden tube pressure gauge for experiment 6. Okay, all of this is our content that includes in this presentation. Alright, for the introduction in this experiment, it says that for an engineer, pressure is such a significant factor that we routinely include it in our calculation. Pressure may also be connected to the weight of a load and its surface area. Many instruments or devices have been created in this world to calculate the pressure value. To measure the pressure of the load in this experiment, we utilize a device known as burden tube pressure gauge. By applying pressure to one of the tubes on the burden pressure gauge, the tube will straighten, causing the pointer on the meter to move to a specified number. Move to the next slide. The purpose in this experiment is to use dead weight to calibrate the burden tube pressure gauge.
Okay, now let's take a look at the application. This experiment requires a burden tube. So a burden tube is used to measure a pressure in a system, providing an visible indication of the pressure level and ensuring that it does not exceed the maximum level or stoop too low. There are many different types of pressure gauge, but this burden gauge is probably the most prevalent. The correct measurement of pressure ensures the system works effectively, protecting other equipment or system in the plant. And almost all modern pressure gauge will be base model from 1849 due to the extreme accuracy, linearity, and sensitivity of the burden gauge. This kind of experiment is widely used in the industry field. So, for example, has a machine and plant engineering, aerospace, gas distribution. It is for check the pressure inside the pipe. Next is marine. Last one is a medical. Now we go to the theory. The burden gauge is the most popular pressure measuring device for both liquid gases because it can be connected to any source of pipe, such as pipe containing fluid. So, the burden gauge itself fitted with a transparent dial which let you see the internal working of the gauge. The gauge consists of a thin wall, closed-ended tube which is oval in cross-section. This tube is bent to an angle of 270 degrees along its long axis. The open end of the tube is welded to a hollow mounting block which allow you pressurized fluid to reach the tube. Next, we go to the apparatus for this experiment. Okay, the most important thing that we need is a burden tube pressure gauge. The next one is a piston and dead weight, which is we use to run the experiment. Next is a parameter and number. Okay, for this parameter and number, we have a piston area, which is shown here, and the plunger and a platform. The calibration constant is in different unit.
The piston was put into the cylinder. The air bubbles were cleaned from the tube. The first reading of the pressure gauge was recorded. Then, a weight of 0.5 kg was put on, and the second reading was recorded. A weight of 0.5 kg was increased, and the third reading was recorded. The steps was continued with all the dead weights provided. Then we continue by decreasing the 0.5 kilogram dead weight one by one, and the reading was recorded for each decreasing dead weight. The steps of dead weight was continued until all the masses are removed.
So this is the result that we obtained from this experiment. As you can see from the table, this is the all of the data that we obtained from the experimental. In the first column, we have mass. that being divided into two, which is mass added and total mass. Both are in kg unit. The second column is theoretical pressure, and the unit is kilonewton per meter square. For the third column, we have calibrated pressure border gauge reading, also in kilonewton per meter square, where we have divided into two, which is increasing order of weight and decreasing order of weight. Both have three different data, so we can calculate the mean for the data, which is, for example, for increasing order of weight, we have three data, which is 36, 35, and 37. So the mean is 36. Same as the decreasing order of weight, where we have 35, 37, and 35. So the mean for this data is 35.6667. Okay, for the last column is the percentage error. It also divides into two, where the first is increasing order of weight, and the second one is the decreasing order of weight. Both these data are we gonna use in our calculation in the next slide. Now we're entering the discussion part. The first question is percentage of relative error for the theoretical and measurement of pressure gauge. A piston of known area is loaded by a known weight. Therefore, the theoretical pressure in the cylinder is, the given formula is F over force over area. So the calculation, we know that the cross-sectional area is 3.1731 times 10 negative 4 meters square, and we know the weight of the plunger and platform is equal to 1 kilogram. So we can calculate the actual pressure exerted by the piston by using this formula, where mass of the piston times the gravitational force divided by the cross-sectional area of the piston. So we sub this data inside this equation, and we get the actual pressure is 30.9 kilonewton meter square. We also can calculate the actual pressure exerted by the total mass, where 0.5 kg is added, and this is the formula, where we only the total mass is 1 plus 0.5, that's equal to 1.5. So the final answer is 46.37 kilonewton per meter square.
Next, we move on to the next discussion part, is to calculate the measured experimental pressure, which is F measure, that can be obtained from the reading of Bourdon tube pressure gauge. Okay, first we have to know that 0.5 kilogram of mass is added, so we must plus the 0.5 kg before in the first part of discussion. Okay, for this one, we calculate the average reading of calibrated pressure with dead weight, which is loading lah. So 30 plus 31 plus 30 kilopascal, then divided by 3 to get the average, and times with 1 kilonewton over meter squared over 1 kilopascal, and then we get 30.3 kilonewton per meter squared. And then after that, we calculate the average reading of calibrated pressure unloading, and then we will get 40 kilonewton per meter squared. And then after that, we calculate the percentage error for both loading and unloading with the formula percentage error equals to the experimental value minus actual value modulus divided by actual value times 100%, and we get for 34.7 per 34.7 percentage for loading and 13.8 for unloading.
For discussion 2, we'll talk about source of error and method to minimize error. The first error is air bubble trapped in the tube, which affect the reading. The solution is remove the bubbles by rotating the piston slightly. The second error is when the dead weight changes, the reading of Bourdon gauge decreases slowly and the piston is not static. So the solution for it is take a reading after a few seconds to ensure the pointer is stable. The third error is parallax error. So the solution is the eye of observer should be perpendicular to the scale of reading. Next, we'll talk about repeatability and accuracy of the experiment. For repeatability, the equipment was displayed by the repeated times under the same conditions, such as the mass added by each time. This is to find average reading because the Bourdon gauge can be sensitive to surroundings, especially the temperature fluctuation. For this experiment, the highest percentage error by comparing both experiment and actual results is 16.44%. This indicates that the experiment conducted might experience the same inevitable errors for fluctuation. For accuracy, the average reading is obtained by repeating the experiment several times to get the most accurate reading with the repeated procedures. When the mass was added to the piston, the deadweight pressure gauge calibration responds slowly and results in the delaying, which is corresponding to the changes of pressure as well as the friction. Although the accuracy and quality of the Bourdon tube pressure gauge have not reached 100%, by repeating the experiment for a few times to get the average reading, the result obtained could be more accurate and more reliable.
As a conclusion in this experiment, the Bourdon tube pressure gauge is monitored each time the wake is raised. The gauge pressure is recalibrated using the dead wake as the gauge accuracy degrades over time. The uncertainties in this experiment might be due to random and systematic error in this experiment's execution. There are several errors that impact the experiment's outcome. To overcome this inaccuracy, the experiment must be repeated numerous times to get an average result. We must also ensure that all of the equipment is in good working order in order to limit the percentage error. Alright, that's all from us. Thank you for watching.